Hello, welcome to this chemistry lecture series. In this video, we're going to look at chapter 17, section 4, which is the last section for the alcohols chapter. Now, in this particular section, though, we're not going to be looking at alcohols. We're looking at an alcohol derivative, which is the carboxylic acid functional group, one of the carbonyl functional groups. So we're going to look at carboxylic acids. We're going to look at some reactions that both make carboxylic acids and that carboxylic acids can undergo. And we're also going to look at the main factor that makes carboxylic acids, which are the fact that they are an acid. So let's get started. Now, the reactions that make carboxylic acids. We already saw one of these in the last video in chapter 17, section 3. And the other one we will see in chapter 18 because it's a reaction of the nitrile groups. But let's review the chapter 17 reaction, and then we'll foreshadow or look forward to the chapter 18 reaction. Carboxylic acids can be made when primary alcohols are oxidized. We already said in chapter 17.3 that a primary alcohol will be oxidized into an aldehyde, and that aldehydes can be further oxidized into carboxylic acids. So we can react both an alcohol that's primary or an aldehyde with a warm acidified potassium dichromate solution, or we could use potassium permanganate, like we always say. Potassium permanganate and dichromate both do the same thing, they're oxidizing agents. But when we react either a primary alcohol or an aldehyde with a acidified potassium dichromate, that has been warmed up, or that the whole reaction is warmed up. So warming is one of our essential conditions here. Then what we're going to get out of that reaction is a carboxylic acid. So this is one way in which we can create carboxylic acids. And of course, the carboxylic acid we create will depend on the alcohol or aldehyde that we are going to start with. So for example, if we were to start with this primary alcohol right here, let me get my pen. So it's 1, 2, 3. So that's propanol, or propan 1O, because the alcohol, the hydroxyl group is on the first carbon. That alcohol would get oxidized by potassium dichromate into propanal. Propanal, which is the aldehyde here, would be then further oxidized by the dichromate into propanoic acid. So whether we start with propan 1O or we start with propanal, as long as we're reacting with acidified potassium dichromate that's being warmed, or acidified potassium permanganate that's being warmed, we would eventually end up with our propanoic acid, our carboxylic acid. So that's one way in which we can create carboxylic acids. The other way in which we can create carboxylic acids is a reaction of the nitrile group that we're going to see later in chapter 18. But just to go over the basics of this reaction, carboxylic acids can be created by hydrolyzing a nitrile group. So remember that nitrile groups are going to be that C triple bond N functional group that we talked about in chapter 14. So when a reaction has a nitrile reflux with hydrochloric acid, so hydrochloric acid and a nitrile is going to be our reactant, what's going to happen is that we are going to essentially grab that carbon, and I'm going to point out the carbon with red right now. So we're going to grab this carbon in the nitrile, the carbon that has a triple bond nitrogen, and that carbon will get a double bonded oxygen and an OH added to it, creating our carboxylic acid. The other thing that we'll get out of this reaction is ammonium chloride as a byproduct from the nitrogen getting hydrogens attached to it and the ammonium ion being created, with the chlorine just being there as a ion that came in with the hydrochloric acid. Now, this reaction does have a special condition. This reaction does need to be refluxed or heated in order for the reaction to happen. So a nitrile will react with a hydrochloric acid and the reflux to create a carboxylic acid, where all we're doing is we're grabbing that carbon in the nitrile functional group. We are getting rid of, let me make this smaller, we're getting rid of the nitrogen and then adding a double bonded oxygen and an OH to that carbon to create our carboxylic acid right here. So the number of carbons on the chain doesn't really change. We have 1, 2, 3, 4, 5. Let me number them. 1, 2, 3, 4, 5. And then in this carboxylic acid, we have 1, 2, 3, 4, 5. So we go from nitropentane to pentanoic acid. So 5 carbons, 5 carbons. We don't add any carbons. We're just exchanging the triple bonded nitrogen for a double bonded oxygen and an OH to create the carboxylic acid in this reaction. We'll look more at the mechanism and how this reaction happens exactly in chapter 18, section 4 later on. So that's the reactions that make carboxylic acids. What about the behaviors of carboxylic acids? Because in the name, we have that carboxylic acids are, well, acids, right? The main signature property of carboxylic acids is the fact that they are acids. So what does it mean to be an acid? Well, acids by definition, as we know since honors chemistry, will lose hydrogens, right? So to be an acid means that it can lose an H+, it can lose a proton, lose a hydrogen ion. So carboxylic acids are weak acids because they can ionize that OH to become O-, to lose the hydrogen and become O-. But they don't do so completely. They only partially ionize. Only some of these will lose their hydrogens, meaning this will be an equilibrium reaction. So because they do not completely ionize or they do not completely dissociate, we see them as weak acids. When we add a carboxylic acid to water, they're going to react with that water, give up the hydrogen, and create both the protonated form, which is when we have that OH, and the deprotonated form, which is when we have that O-. So we can call this the protonated form. Oops. And this is the deprotonated form of the carboxylic acid. Protonated just meaning that it has a proton or hydrogen ion. So protonated means it has the H. Deprotonated means it does not have the H. And when exactly does it and does it not have the H? Well, that is going to be dependent on whether or not it has an acidic condition or a basic condition. Under acidic conditions, a carboxylic acid will be protonated. Because in acidic conditions, there's more than enough hydrogen ions to push this equilibrium towards the left, giving us a protonated form. But under basic conditions, when there is a low amount of hydrogen ions, the equilibrium gets pushed to the right, giving us more of the deprotonated form. So this is important because carboxylic acids, we said this earlier when we were talking about the hydrolysis of esters. Carboxylic acids cannot exist unless they're in an acidic condition. Because if they're not in an acidic condition, if they're in a basic condition, the hydrogen ion concentration is low and the equilibrium gets shifted towards the deprotonated carboxylic acid. Meaning that most of the carboxylic acid is not going to be a carboxylic acid, is going to be what we call the carboxylate ion. So under basic conditions, carboxylic acids exist as the carboxylate ion, which is the deprotonated form of the carboxylic acid. Under acidic conditions, the carboxylic acid exists in its protonated form, which is its carboxylic acid as we would normally see it, with the carbon double and oxygen, OH. So the H is still there. Now, because carboxylic acids undergo all of the usual reactions that acids can undergo, there's actually three main, what we call acidic reactions of carboxylic acids. And those are the fact that carboxylic acid can undergo acid-base reactions with an alkali, so essentially a neutralization reaction with a base, to form a salt and water. They can undergo the reaction with a reactive metal like sodium, like what we saw with sodium and alcohols earlier in section 3, to form a salt and hydrogen gas. And they can undergo an acid-base reaction with carbonic ions, like sodium carbonate, for example, to create a salt, water, and carbon dioxide. So let's look at those three reactions. Let's look at the acid reactions of carboxylic acids. So, like I said, there are three reactions that carboxylic acid can undergo. And it doesn't matter what carboxylic acid we are looking at, because the focus of these reactions is always going to be the hydroxide. The hydroxide is where the acidic proton in a carboxylic acid lives. The acidic proton in the hydroxide being that hydrogen in the OH. That's a hydrogen that gets lost here. So what happens? The only difference between all three of these reactions is what other than the carboxylate ion is created. During an acid-base reaction with an alkali, the carboxylic acid reacts with something that has hydroxide in it. So what happens? The hydrogen and from the carboxylic acid and the hydroxide from the base create water. Just like in any acid-base reaction between an acid and an alkali. The other thing that will happen is that our carboxylic acid, I'm going to highlight this in blue, our carboxylic acid, other than the hydrogen, will create our carboxylate ion. Notice that's exactly the same compound. It is the carboxylic acid minus the hydrogen, so we get a negative charge instead. So our carboxylic acid, whenever it undergoes these acid reactions, any of them, it's going to just lose its hydrogen and become the carboxylate ion, the O- ion. So this propanoic acid becomes propoxylate ion. And then if there's a positive ion, which in this case there is, that potassium from the potassium hydroxide from the alkali, which is positive, it's going to be attracted to the negative carboxylate ion and they're going to pair up. All right, but notice that carboxylate ion is going to be the main chunk of organic compound here. If we have the reaction of the carboxylic acid with the reactive metal, again, because the acid is acting as an acid, the reaction will still create a carboxylate ion. Anytime a carboxylic acid acts like an acid, it creates a carboxylate ion. So this right here, this whole chunk of carboxylic acid, except for the hydrogen, because that's what's being removed in a reaction where it acts like an acid, it's going to create this carboxylate ion right here. And the only thing that will change is what's around it, what attaches to it, what other compounds are created. The hydrogen in this case, that is lost, and there's a reason why there are two carboxylic acids, that hydrogen is going to go to creating hydrogen gas. And then the sodium, which is what we had reacted this carboxylic acid with, in this case, and it could be any reactive metal, so it could be sodium, lithium, it could be rubidium. But that sodium, or whatever the metal is, will become the +1 ion that it creates, again attaching itself to the carboxylate ion because the carboxylate ion is negatively charged. Now, when we react these reactive metals, though, we do get one observation, and that is that the hydrogen gas can be seen as bubbles as an observation to this reaction. So if I were to drop a chunk of sodium into, let's say, propanoic acid like this, we will see the sodium starting to bubble as hydrogen gas gets created. And then the last reaction, again, which is an acid reaction, is going to be the reaction of that carboxylic acid again with a base, but this base is slightly different. It's not an alkali, it's not a water-soluble base. It's going to be with a carbonate to form some different compounds. So a carbonate, remember the carbonate ion is a CO3 ion right here, CO3 2 minus. And that's how you pair up with some metal. What happens here is an acid-base reaction, which is the same as any reaction of a carbonate with an acid. We are going to create, because carboxylic acid is acting like an acid, the carboxylate ion again. So when I create the same carboxylic acid but with a minus sign on the oxygen, and then the carbonate reacts with the hydrogen ions and creates two things. It creates water, which is where the hydrogen ion from the carboxylic acid came from, along with some of the oxygens from the carbonate ion. And it's going to create carbon dioxide. Again, because we have carbon dioxide, which is a gas being created, we are going to have bubbles as one of our visuals, as one of our observations. So this one also bubbles, but the bubbles in this reaction are of carbon dioxide, whereas the bubbles in this reaction are of hydrogen gas. And then, of course, that positive ion, that potassium that was with the carbonate, that is still hanging around. So it's going to be attracted to the carboxylate ion when the carboxylate ion gets created, because they have opposite charges. They create an ionic bond. So these are the three reactions where carboxylic acids are acting like acids, where it's losing the hydrogen, creating the carboxylate ion, and then depending on whether it's reacting with an alkali, an active metal like sodium, or a carbonate, it will create different other products, either water with the alkali, hydrogen gas with the reactive metal, which shows up as bubbles, or water and carbon dioxide with the carbonate, which also the carbon dioxide shows up as bubbles. And whatever positive metal ion we have from this reactants, that positive metal ion will get attached to our carboxylate ion, which has the opposite charge. So that's another three types of reactions that carboxylic acids can undergo. Let's look at the last reaction in this chapter, which we actually already looked at kind of, but we went in the opposite direction, we went backwards. We saw earlier that a primary alcohol can be oxidized into a aldehyde, and that aldehyde can be oxidized into a carboxylic acid. Well, if that's the case, if that oxidation reaction can happen, then the reverse reaction can also happen with reduction. Because remember, reduction and oxidation are two sides of a coin. They're opposites of each other. So if we can oxidize a primary alcohol to an aldehyde, and that aldehyde to a carboxylic acid, then it stands to reason that we can undergo the opposite process to grab that carboxylic acid that we created, reduce it into an aldehyde, and then that aldehyde can be further reduced into a primary alcohol. And that's exactly the case here. We can react carboxylic acids with a reducing agent. In the case of this reaction, the reducing reagent that we use is tetrahydroaluminate, or LiAlH4. Tetrahydroaluminate is one of the most common reducing agents that we have in this curriculum. It's essentially the potassium permanganate or potassium dichromate of reduction instead of oxidation. Now this tetrahydroaluminate needs to be in dry ether when it's used. So it cannot be in water, it cannot be aqueous, it has to be in dry ether. It has to be in dry ether because the LiAlH4 can react very violently with water itself. So we never have aqueous LiAlH4. It's always going to be in dry ether. So this is not specific to this reaction. This is just any time we use this particular reactant, it's always in dry ether. What the reaction essentially does is the exact same as the oxidation reaction we saw before, but backwards. So this reaction is going to grab that carboxylic acid, and then it's going to reduce it into an aldehyde. And if we don't do any distillation, if we keep the aldehyde there, it will then keep further oxidizing into a primary alcohol. We can only make primary alcohols in this way. We cannot make secondary, tertiary alcohols because those don't oxidize into carboxylic acids. So the carboxylic acid cannot be reduced into them. So we can show the reaction with a simplified notation of H in brackets. We've seen this before. So instead of writing the LiAlH4, because it's a reduction reaction, we can simply just use the H in brackets to symbolize the hydrogens provided by the tetrahydroaluminate. When that carboxylic acid gets oxidized all the way, it will create a primary alcohol which has the OH where that carbon-double-bond carbonyl group was. So essentially all we're doing in this reduction is getting rid of the O double bond carbon. So this we get rid of and we end up with the primary alcohol. This of course happens in two steps. So this happens by first reacting that carboxylic acid into an aldehyde in the first reduction, and then that aldehyde into a primary alcohol with the second reduction. So we go from a carboxylic acid to an aldehyde in the reduction. And that aldehyde then, if it sits in that LiAlH4 in dry ether, will get further oxidized into a primary alcohol. Just like with the oxidation, if we wanted to prevent this last step, if we wanted to say, no, we do not want a primary alcohol, we want to stop this right here and get the aldehyde, we will do distillation, which will remove the primary aldehyde from the mixture and therefore not let it keep reacting. So that's the reduction. It's exactly the opposite of the oxidation we saw in the earlier chapter. And it's what I use tetrahydroaluminate, which is the opposite or the counterpart to potassium permanganate or potassium dichromate. It is a strong reducing agent instead of oxidizing agent. So that's the last reaction in this chapter for both carboxylic acids and alcohols. This flow chart, and I know it's a lot, but this flow chart shows every single reaction that we just saw in this chapter. So we saw the reactions early on of alcohols with things like sodium hydroxide, of halogen alkanes with sodium hydroxide to make alcohols, or the reaction of alcohols with either PCl5, PX3, which could be PCl3, PBr3, or PI3, or SOCl2 or HX to make a halogen alkane. We saw how alcohols can get combusted into carbon dioxide and water. We saw how alcohols can react with sodium to create an alkoxide ion and hydrogen gas. We saw how alcohols can be made into alkenes by the use of heat and Al2O3. And then we also saw earlier in a different chapter how those alkenes can be turned into diols, which are a type of alcohol, by using dilute potassium permanganate. The alkene can also be turned into alcohol by using steam and phosphoric acid. and that alcohol can be turned into ketones by reduction, by oxidation, and then the reduction of ketones can produce secondary alcohols. Alcohols can then be turned into esters, aldehydes, carboxylic acids, which all have their own type of reactions. So this is just putting everything together, dealing with alcohols, carboxylic acids, and esters. Obviously, this can then be chained with the flow charts that we saw in other chapters to figure out other pathways. And that's what's important here. If I wanted to go all the way from a halogen alkane to a diol, that might be a question on the test. And it requires three different reactions. It requires the halogen alkane being turned into an alcohol using sodium hydroxide and reflux, the alcohol to be turned into an alkene by using heat and aluminum oxide, and then the alkene being turned into a diol by using dilute potassium permanganate. This is what these flowcharts are for. They're not for you to memorize every single reaction, although you should try to, but they're for you to visualize how one functional group can be turned into others through a multi-step reaction. How halogen alkanes can be turned into carboxylic acids by turning them into alcohols, then aldehydes, and then carboxylic acids in a series of three reactions, what we call reaction series. So this is just food for thought on how we can use these charts to navigate reactions and very complex reaction chains in organic chemistry. Well, that's it for for chapter 17 and for section 4. We have one chapter left in the curriculum, which is going to be chapter 18, which we're going to look at carbonyl groups. So I'll see you once we start that chapter in the next video. Thank you for watching.